All right, so this is Math 317 Operations Research. This is lecture 28, the GaleShapely algorithm. This led to a Nobel Prize in economics. It appeared originally in the American Mathematical Monthly. This is a really nice, readable journal. The articles there are extremely well written. They're often on interesting topics. This not only turns out to be an interesting topic, but a topic of tremendous real-world applications. You're trying to do a matching problem. You have some people in column A, you have some objects in column B, and you want to figure out, how do I assign the stuff in such a way? And what might you want to have in your assignments? What kind of goals might you have? So think of it as, I have students applying to college. What might be your goal? Get all of them into college. All right, everybody comes to Williams. There we go, we've solved the problem. So what might you put in as secondary goals? We can get them all into a college that they want to. All right, everybody gets to go to their first pick. What might be another goal? I'm sorry?
They can go to all different schools.
Well, so I mean, if I just give everybody their first choice, everybody gets to go to college and every student is happy. Yeah, the school, okay, so one is the schools might have a limit. What else might there be as an issue? Yeah, the students may not meet the requirements to go to the college. It may not be a good fit for the college. So unfortunately, you're going to be pulled in different directions. If you want to try to maximize student happiness, that's pretty easy. If you want to maximize college happiness, a little bit harder, but we can do that. And then the question is, where do you draw the line? How much do you trade off? There are stories, and I know at least some of them are true because they've led to federal lawsuits, where colleges have colluded and have gotten together and coordinated aid packages to students. Why might colleges do this?
Get every last dime out of there.
Yeah, get every last dime. Let's not get into a bidding war. We'll take this student, we'll offer this student a good package, and nobody else offers them anything. And then you want this, and then we'll give you this student, we won't give them any package. And so if you can coordinate along those lines, the colleges can arrange it so that they have a much better chance of getting the students they want at an affordable amount for themselves. So this work by Gale and Shapley was, was extended by Alvin Roth, and it led to the two of them winning the Nobel Prize in economics. Gale was dead at this point, so was not eligible to win. Here are just three different places where it's used. So assigning new doctors to hospitals, matching residency. So you have a bunch of people who have just gotten their doctorates, you have a bunch of hospitals who need new residents. How do you determine who goes where? And there's been a lot of extensions of this over time. One of the new extensions was to allow people to try to go to a hospital and be matched to a hospital with a significant other. I want to come to your hospital, but I'm in a relationship, I'd like my spouse to come as well. Or maybe my spouse doesn't have to come to your hospital, but my spouse has to come to a hospital in the same city or maybe within 40 miles, something like that. And so there's been generalizations for that. Another great one is pairing students to public schools. So, a lot of times there were assignment processes. How do you determine who goes to which schools? A lot of efficiencies were realizable here. Another really nice one is helping transplant patients find a match. So if you're interested in any of these topics, there's a lot of very readable articles. I've just linked to a few of them over here. And here's the canonical example. And so the person who was writing the article enjoyed the book Pride and Prejudice. I don't know if anybody here has read that. I will not say my comments on the book while the camera is recording. But so 4 ladies from Pride and Prejudice: Elizabeth, Jane, Lydia, and Charlotte. I remember Elizabeth. I think I vaguely remember Charlotte, and that is about it. 4 men, I think Bingley, Darcy, Collins, and Wickham. I only remember Darcy. And so each person ranks how they feel about the others. And then we want to somehow match so that each woman is matched with a man and each man is matched with a woman. Now, what's nice in this situation is we have the same number of men as women. Will it be possible to come up with a match? Yes. Will it be possible, do you think, to come up with a matching where everybody is as happy as possible? Maybe. So what do you think it's going to depend on? What do you think will make it from a maybe to a yes or a maybe to a no?
If each first choice matched to the other person's first choice.
Good.
The person's first choice was also there.
Good. So if we usually use capital letters for men and lowercase for women or vice versa, or regular letters, Greek letters, something so that you can quickly look down and see which are the differences. So if there's perfect alignment in matchings, then everything should be fine. If your first choice is such that that person is your, so if my first choice is A, but I'm A's last choice, we know we're in trouble in terms of maximizing, in terms of getting everybody their top choice. Not going to happen. What do you think our goal should be?
Maximize first choice pairs.
So one is to maximize first choice pairs. So why first choice pairs?
I think you should minimize the distance from first choice for each pair. If you maximize first choice pairs, there's still great.
Okay, so I am deliberately trying to have a discussion on this and not just go to the math. The math is actually very straightforward. What's not so straightforward is what you want to apply the math to. What problem do you want to solve? Why do you care so much about first choice?
Because that's the feature that I said.
So one of the problems is if I just give you first choice, second choice, third choice, fourth choice, there's some information I'm not giving you. What information am I not giving you? Right, how much more do I value? If I'm going to spend all of this time maximizing first choice, but I'm really, okay, look, you want me to choose someone as my first choice. I really don't care between Darcy, Collins, and Bingham. I just don't want somebody whose name is, late in the alphabet. And so I'll just choose one of the three of them semi-randomly, then the next, then the next. And all three of them I really like a lot. And I just hate Wickham. In a situation like that, if you don't give somebody their first choice, your system will ding you a bit for that, but really it shouldn't be that much. So one of the difficulties is how much information do you want to collect from people? The more information you collect, the better you can do. What you could do is you could give somebody 100 tokens and say, allocate the 100 tokens. And then what might we try to do? Okay, so let's say you know that we're trying to maximize the number of tokens. What might you do? You have to allocate your tokens. Would you like to be Darcy? Okay. I think the only line I remember is, oh, no. She is not pretty enough to tempt me. I will never marry. So how might you allocate your tokens if you were Darcy? And remember, you know that I'm trying to maximize the number of tokens each person gets in the assignment. And let's assume everybody is honorable but you.
75 to Jane.
Okay. Why 75? Okay, so why only 75?
I want to have room to sprinkle.
So one possibility is to give a lot but not all to Jane and try to protect yourself so that if you don't get your first choice, you then protect it a little bit in what comes next. What's the other strategy? Yeah, go all in on Jane. And if you know that the algorithm is going to try to maximize how many tokens you get, If you put 100 on Jane, then when I'm running the algorithm, all right, Paul really wants, Darcy really wants Jane. I've got to make sure Darcy gets Jane. And if everybody else is spreading the tokens, semi-uniformly, or maybe with a little bit of a preference one way or the other, you could really succeed in a situation like this. One of the assumptions, what do you think we have to assume when people are assigning their values? So imagine we were doing tokens and we're doing the mathematical analysis. What would you have to assume about the token assignment?
Based on how they feel.
That's right, right. Would you like to make that assumption in the real world? No. If people are interested later in the semester, we can talk about divorce proceedings and how to play games like this to try to maximize what you can get out. I hope this will only be of theoretical use to you all. But just, in situations like this, if you don't trust the information people are going to give you, there is a real danger of your algorithm running and giving you a bad outcome. And that's why I really want to spend time talking about the problem and not just going into it. We can go through the math very quickly, but thinking about what do we want to apply the math to, what problem do we want to solve, and depending on how we choose to do it, we can get very different answers. And if people know that the system can be gamed, it will be. Is anybody familiar with the women's badminton Olympic scandal from maybe 8 years ago, give or take? So they warned the Olympic Commission beforehand that you have set up an incentive structure for teams to not always play their best. And they ignored them. And one of the Chinese teams realized that if they deliberately lost, they would still make it to the next round. But if they won, they would have to play another team from China. So they deliberately lost. Well, when they deliberately lost, other teams then started to deliberately lose as well. And you ended up having 4 teams deliberately throwing games. I mean, they were hitting the ball straight down. They were serving deliberately. They were making it clear that they were throwing the match. I believe 4 teams were eventually disqualified. And they had all done the calculation that it was in their interest to lose. Yep, and so in basketball, if you are basically not going anywhere towards the end of the season, you might be trying to get the best draft pick. And so a lot of times teams will, what's the phrase? Give other people a chance to show themselves and right, rest their starters. But this is one of the reasons why in basketball now, you do not get a guarantee of the best draft pick if you have the worst record. They have the lottery now. But in football, you still get the best draft pick if you have the worst record. And so in football, there's absolutely an incentive at the end of the season to lose. And so you've got to be really careful in whatever system you set up, what problems is it going to lead to being solved? So if we know that we're trying to maximize the tokens, then people have a tendency to cheat. Now, of course, if you put all of your stuff on Jane and you don't get Jane, now you've lost all chance of having your second choice that you like a lot. So it might be better for you to do somewhere maybe between 75 and 90 tokens on Jane and have some reserve so that, okay, if you don't get Jane, at least you'll get your second choice. This is the advantage of just ranking people 1, 2, 3, 4. Is, we don't know, unfortunately, how much, Darcy prefers, Elizabeth to Jane to Charlotte to Lydia. We just have a relative order. And so we don't know if it would be terrible for Darcy to get Elizabeth or for Darcy to, versus, how much better that would be than getting Jane. If you can trust people, it's of course better to have tokens and put that in. I do some online math REUs over the summer where we have students, assign tokens and whatnot. And you have to assign a certain number of tokens, and you can only put so many tokens in a given bin. So you can do something like that. You can't put more than, say, maybe 50% into your top choice. Okay. Do we want to have everybody rank everybody? Yes. It just makes it much easier when we're doing the comparison. If there are ties, it makes things a little bit harder. So we will assume that there is always a way to determine who you prefer. There is some category. Did I ever tell you the story about the helicopter mom I met when I was a postdoc at Brown. Anybody remember how many letters of recommendation you used for college? 2. Anybody want to guess how many she arranged for her son? Okay, I have 8, 5, 8, 5, and 6. So 14, 19. If you doubled the sum of all of your numbers, that's below what she had. She had over 40 letters of recommendation for her son. If it came down, though, between someone else and her son, and the deciding factor was how will you brush your teeth, she had arranged for a letter of recommendation from the dentist who talked about his daily flossing and side-by-side motion. We will assume that there is some category, if we go far enough down, that will distinguish each option so that we don't have ties, we have a distinct ranking. Okay, now again, it may be the case that we really are indifferent essentially between 2 options, but we will keep it this way. Okay, so any questions on the problem? We have 2 different groups and we want to somehow relate, we want to match. And again, there's lots of different generalizations. You just went through pre-registration right now, where we're trying to match students to classes. So again, there are lots of examples of problems like this. Okay. So one of my favorite toys or mathematical objects is the Rubik's Cube. Right. So went online and found an image of a hopefully correctly mixed up Rubik's Cube and a solved Rubik's Cube. I have not checked to see if this is actually a physically realizable state. I will assume it is. Do you think it's possible to solve a Rubik's Cube using techniques from this class? And if so, what techniques do you think we might have that would solve a Rubik's Cube? So again, whenever you have a problem, the first thing is, do I have a way to solve it? Then, if the answer is yes, is that a good way to solve it? So for the Fibonacci numbers, I can find the millionth Fibonacci number by just adding, but it's going to be very painful. I can use Binet's formula and jump to the solution. Any thoughts about what could we use from class to solve this? What techniques? So what have we learned that might be useful for this? Okay, so what technique are you using? What method? Okay, but what method? What method from class? We spent a lot of time on this method. Okay, and where does this come from? The simplex is how you solve what kind of problems? Linear optimization, linear programming. Can we do this as a linear programming problem? Yeah. So what you can do is you have different moves. This is similar to the frog problem or to the traveling salesman problem. At each moment in time, we do a turn. And then maybe the objective function, what we're trying to optimize, is whether or not the cube is solved. Now, one of the things that's nice, and we're not going to necessarily see it on here, is whenever I turn any face, I do not change the relative ordering of the centers. So it's a little bit unfortunate here that it's oriented with the yellow on top and the blue coming out on the left, whereas here it's the red on top and the white coming out over here. But I can always keep my cube fixed in space so that the relative ordering of the centers does not change. And what I can do is I can check after a series of moves, in my new state, is this piece the red, white, blue piece? Is this piece the red, white piece? Is this piece the, so red goes opposite orange, white is opposite yellow, so it'd be, red is opposite orange, white is opposite yellow, so that would be the red, white, green piece over there. And I can just go on and on and on. I can say, if at time t, all of these pieces are correct, that I have a value of 1. I've got my cube solved. And if at time t, I don't have every piece in the right spot, I have a value of 0. And then I just go at every moment in time, I calculate, is the cube solved? And let's say I'm willing to do n turns. I then just take, this, let's just say if the sum is greater than 0, it's a 1. If the sum is not greater than 0, it's a 0. And my objective function is I want to maximize the indicator of that sum. And so if the cube is solvable, then I will be able to, at some sequence of moves, get it there. This will be an integer programming problem. This is going to be a painful way to solve it, but it will solve the cube. In Rubik's cube theory, there's something which is known as the God's number. If you give the cube to God, how long would it take God to solve? So the God number for the cube is 20. I can't remember if this is what type of moves you allow. So for instance, if I spin one side twice, is that 1 move or 2 moves? You only have to worry about turning things to the right because if I turn things to the right 3 times, that's the same as turning it to the left once. So you have to be very careful as to what are you defining as a move. So I forget exactly how it's defined. It's not really that important, but we could solve this as an integer programming problem. Could we do that for the matching game? Could we solve this? Well, let's think of what we want first. The first is we want a matching where everybody is assigned to somebody. And then what would you have as your objective function? This is the hard question.
Like what we're looking for in an objective function.
That's what you have to choose. You have to decide what is going to be considered a success for you. What are you trying to either maximize or minimize?
The ranks or that each one gives for the matches that happen.
Okay, so for each match that happens, there's a value from the men, there's a value from the women. We can just add up all those numbers and we can say we want that total sum to be as small as possible. And so we could then set up a linear programming problem, go through all feasible solutions. Feasible solutions would be solutions where someone is matched with someone. And then just look at which one or which ones have the smallest sum. So we can solve this with linear programming. So is there really any need for these dudes to come in and come up with a new theory? I mean, we can solve this with linear programming. We can solve the Rubik's Cube with linear programming. Just because we can solve something one way, does that mean we should solve it that way? Why not? It will take a long time. How many people have taken probability? We did Newton's method in divide and conquer, right? So by using more information about the problem, Newton's method uses calculus, it uses the derivative, it gets a much better convergence rate in general than divide and conquer. And so when we try to use something extremely general like linear programming, it may not be the best tool for the specific problem at hand. And this is why we have a whole slew of tools in operations research. Depending on the structure of your problem, some things are going to be better than others. And so even though we could do both of these problems by linear programming, you should never, ever, ever do these problems by linear programming. And we want to develop a better procedure. And in fact, not only does their algorithm give us a nice explicit construction, but it's fast. If you have n people, it takes less than n squared steps to find the solution. This is extremely rapid. Okay. So a couple of definitions. So an assignment of applicants to colleges will be, and so again, it's either applicants to college or marriages, depending on what language you want to do. I'm just pulling things directly from their paper. So an assignment will be called unstable if there are two applicants, alpha and beta, who are assigned to colleges A and B, such that even though beta prefers A to B and alpha prefers, anyway, okay, it's unstable. So here, let's draw it. This down a little bit. And so what do we have? So we have alpha and beta assigned to A and B. So here's A and B, and here's alpha and beta. So they're matched together. But we know beta prefers A to B, and alpha prefers B to A. Well, if that's the case, what should we do? Switch them. So if we do that, all we need to do is switch. Basically, what this is saying is it's unstable if two different pairs can just mutually get together and say, hey, we'd be better off if we just traded. Why don't we just trade amongst ourselves and then present it to the rest of the group as a fait accompli? So we are the last bastion of you must learn public speaking before graduating. Our department is holding the line, and students have to choose a colloquium date. Sometimes things happen. If you come to the colloquium stars and say, hey, I can't do my time, but I've already talked to so-and-so and they can switch with me. Sure. You've made the problem very easy for us. Absolutely, just switch. Not a big deal. So this is a great example of instability. That if you ever have situations like this, then you're going to just have some peers just get together on their own and say, we're going to just swap and make things better for everyone. Well, okay, better for ourselves, and so better overall. Is it possible that you could have the pair A alpha involved in multiple pairs where alpha would rather go and A would rather go? Could we have another school C and gamma, and maybe alpha prefers C to A and gamma prefers A to C? Is that possible? What I'm saying is, could there be multiple pairs that might want to switch with your pair? Of course. And then the question might be, which pairs switch? And then it could become interesting because, well, I'm happy to switch with the B beta pair. I'd also be happy to switch with the C gamma pair. For me, alpha would rather switch with the B pair, but A would rather switch with the gamma pair. So you could easily have a situation like that where you have multiple candidates to switch with, and you might disagree with your match as to whom should you switch with. So it may not be immediately clear which way you'll switch, but at the very least, a switch will happen. Okay. So a stable assignment is called optimal if every applicant is at least as well off under it as under any other stable assignment. So the question is it always possible to find a stable matching? And if there's a stable matching, is it always possible to find a optimal one? So let's take the optimal one. Do you think we'll always be able to find an optimal matching? Or might there be a situation where some people are not as happy in this stable matching as they would have been in another? But it's not the case that everybody is happier. So we talked a little bit about this with assigning students to colleges. What's one simple way to do the assignment? Give every student their first choice. Okay, in that situation, would that be stable? Would any student want to switch? But maybe the colleges are not getting their first choices, so maybe the colleges would want to switch. And you could look at the stable matching where each college takes their first choice. And we'll assume that no two people have the same first choice, no two colleges have the same first choice. And so if each college takes their first choice, the colleges are now happy, but the students are not. So it's not too bad to find stable assignments which are not going to be optimal. So it seems like finding something that's optimal is going to be very hard. And because it's very hard, this means we are going to have to decide what is the goal? What is the objective? In linear programming, we have an objective function that we want to maximize. Maybe it's cost, maybe it's travel time on a bus, something. Over here, it's not as clear what we want to do for the maximization. So the other question that's really written here explicitly, is it always possible to find a stable set of marriages, a stable assignment? And the idea you would almost hope is that there's no cycle that would happen, is that if I just maybe if I randomly assign people and just let people keep switching, but maybe it's possible to come up with some kind of cycle of assignments where you'll have peers switching. So as a nice extra credit assignment, see if you can come up with a cycle where you have maybe 3 people so that 2 peers are always willing to switch. And so if I start with this kind of assignment and I allow them to keep switching like this, I won't end up getting into anything that's stable. Maybe you can't do it with 3, maybe you have to do it with 4 or 5, whatever. It turns out that there is always going to be a stable matching. There will always be an assignment so that you can't find 2 pairs that can go off by themselves and say, hey, let's just switch internally amongst ourselves. That doesn't mean you can't find 3 pairs that would be willing to do it, but it just means that you can't have just 2 people doing it on their own. Now, of course, what you might have is maybe alpha prefers B, and maybe, so alpha prefers B and B prefers alpha. So they could just say, hey, let's screw our partners. I'll take you alpha and we'll shove beta to A. So you could have something like that. And then that would make alpha and B happier, but make A and beta less happy. Okay. So here's a nice example. So the following is a ranking matrix of 3 men, alpha, beta, and gamma. So these are going to be the men. And A, B, and C are going to be the women. Okay, so the first number gives the ranking of the women by the men. The second number is the ranking of the men by the women. So thus alpha ranks A first, B second, C third, while A ranks beta first because the 1 is there. So can somebody give me one matching? So what's one possible matching? Okay, how are you choosing your match? You've got to tell me which man goes with which woman. You got to give me all 3 assignments. So can you give me a nice procedure that will give me an assignment? Okay, why? By whose ranking? Okay, so give me the rule that's giving you this.
I'm trying to keep the rankings as close together as possible, so we both like.
Okay, so you want to send alpha to B? Okay, so this is maybe like the average ranking. So we would have A, B, C, and we would, oh, sorry. I'm using blue for women. So we would have A, B, C, and for the men, it would be B gets alpha, right? C gets beta, and A gets gamma. Okay, so that's one possibility. What's another possibility? So you try to keep the average.
Just give all the women the first choice.
Okay, so women get first choice. And of course, to be fair, then we should have men get the first choice. And so if we do the women getting the first choice, then A's first choice is beta. B's first choice is gamma. So C's first choice must be alpha. And if we do the men get their first choice, A would get alpha, beta would get B, and gamma would get C. So notice we have three very different matchings. So depending on whose perspective you adopt, you can get a very different answer. And all three of these are legitimate defensible positions. Of these, which do you think would pass the fairness muster the best of these three proposals? I think there's a clear winner of these three. Yeah, the average ranking, because as soon as you say, let's give the women, why is it the women? Let's give them, why the men? So the average ranking seems to me the most easily defensible one in a situation like this. Now, of course, it's not always going to be the case that you'll be able to get all these matchings to work. Okay, and so we could go through and calculate lots of different ways. Skip that for now. And so here are the two big theorems from the paper. The first theorem one is there always exists a stable set of matchings. And the second is every applicant is at least as well off under the assignment given by what's called the deferred acceptance procedure as he would be under any other stable assignment. So the question is this the same as saying we have something that's, optimal? Is this the same as saying that all the players are happy? Every applicant is at least as well off under the assignment as he would be under any other stable. Does that contradict what we did earlier, where we said, wait a minute, no, we have situations where not all the players are equally happy? So there's a key word here. What is the key word in theorem 2? So every applicant is at least as well off under the assignment given by the deferred acceptance procedure as he would be under any other stable assignment. Nope. Nope. When we looked at students going to colleges, could we come up with a situation where we have something that's stable, but not every player is happy? What were those situations? Okay, so if the colleges choose their first choice, the colleges are happy, but the players are not. And in fact, there was another stable matching where the students choose first, where they're happy, and the college is not. So what's the key word here? Every applicant is at least as well off under the assignment given by the deferred acceptance procedure as he would be under any other stable assignment. No, that's the procedure. Is every player happy as possible?
They have a situation that couldn't be any worse. Is it at least?
No. So in the colleges and the students, was everybody equally happy? So over here, am I saying everybody is equally happy? Who am I saying is happy? The applicant. There's an asymmetry here. The key word is applicant. So again, I really want to go slowly and talk about how do you read things? When you're reading a statement, what are the key words? The key word here is every applicant. It's not saying every player involved. That would be very different. So we already know that there are different stable assignments. And we can have the stable assignment that's college-centric. We can have the stable assignment that's student-centric. Or for marriages, that's men or women-centric. And so depending on which choice we make, depending on which perspective we adopt, some people are clearly going to be ecstatic, while others are going to be upset. And so theorem 2 is not saying we're going to come up with something so that everybody is as happy under this as they would be under anything else that's stable. It's just saying if we choose a team, if we want to do things from their perspective, we can do things in such a way that they will be happy. And that there's no other choice that would make them happier. So for example, if you wanted to maximize the happiness of the women, what would you do? Yeah, maybe give women their first choice. And then over here, if anybody's interested, I've just posted some stuff. The global mean matching, the global median and the local median matchings. This is basically trying to come up with a situation where there's not just one option. There's several different options that will be stable. And we're trying to come up with ways to decide which one do we want. So in linear algebra, when you're trying to solve a system of equations, typically how many solutions are there? One. Normally, you have AX equals B, A is a square matrix, A is invertible, there's one solution, X equals A inverse B. So when you're trying to do linear algebra, typically, you're not going to have multiple solutions to choose from. When we get to linear programming, we often have multiple solutions, and now we can try to decide which solution is going to be best in some sense. And it's only when you have more than one solution that you can start trying to put in a notion of best. And so over here, when we start looking at there is more than one stable matching, okay, we need some way to decide how to rank the different stable matchings. Median is a really good example. So extremes are kind of mellowed out a little bit. And so if we have multiple things and we have some way of saying which one is in the middle, maybe that's kind of splitting the difference, and that's a good thing to go for. And so, if you want to, you can read, there's just like a little paragraph about each one. And there's a surprising fact that there's always going to be at least one of each of these, and they're going to be identical. And so if you accept these as notions of fairness, there's actually ways to find them. And again, this is extremely important for applications that you can tell people, we are now going to assign who gets the organ transplant. We're going to assign who gets into which schools. You want to be able to say, this is a fair procedure. All right, so I'm going to just state the theorem, and then if people are interested, we can go through and prove it in detail on Wednesday. So the theorem is, there's always a set of stable matches. And the way it works is each boy proposes to his favorite girl. So it's possible that some girls could receive multiple proposals. It's possible that some girls receive no proposals. And when a girl receives proposals, she doesn't accept. She takes all the proposals she gets, and whichever one she likes the most, she says maybe. And everyone else she says no to. And then all the men who have not received a maybe propose to new girls. They propose to the highest option still out there. And then the women look at the proposals that come in, and then they say maybe to the highest one. You keep doing this until everybody has a proposal. As we have the same number of men and women, if there's ever a woman who does not have a proposal, she has no maybes, there's got to be at least one man who has to still propose. And so you just now have to go through and show that this will terminate in a reasonable amount of time. They say that it will terminate in the most like n-1 squared steps, so it'll terminate very quickly, and that it'll be stable. So again, if people are interested, I'm happy to go through and do the algebra. I just wanted to show you there's a really nice idea behind this. This is essentially a Nobel Prize in economics. Yeah. just a couple of paragraphs. It doesn't have to be long and involved. If you can find a way to use good mathematics to solve real world problems, it's phenomenal. So this is a good place to stop. Stop the recording.